could the people please, for those who may have forgotten, shut their microphones? Thank you.
Okay, so we're starting this third. So we're in this third day of the 20th DRAKKAR meeting, and we're about to start our third keynote lecture. So as we discussed over the previous 2 days, so we've tried to propose keynote lectures coming from recently published work and covering all the sort of activities that we believe were worth discussing within this workshop. And in discussion with the scientific committee, we decided to cover aspects related to the use of ocean models for designing and using ocean observations, the use of ocean models for better understanding the processes and the physics, but also aspects that are more related to the underlying foundation of those ocean models we're using. And we're here today about to hear from a talk I'm very glad to introduce. So we're going to talk about probably something that you guys may find a bit provocative or disturbing or new. And I'm very glad that we have here Dion Häffner with us. He will discuss about like new paradigms in ocean modeling coming from differentiable programming, and trying to explain a bit what sort of benefit we can get out of it. Dion is an early career researcher, still a PhD candidate at the Niels Bohr Institute. So I thank you for being very supportive and welcoming, in particular during the discussion session. I'm very glad that you have here, Dion, and that you've accepted to give this lecture, and I hope we'll have an interesting discussion afterwards. As for the previous keynotes, we'll have like something like 25 to 30 minutes for your talk, and then a 15-minute discussions, which I hope would be active. And if you have any questions as the talk develops, you may start typing them in the chat, and I'll make sure to collect them and make the discussion at the end of the presentation. So welcome, Dion. We're very glad to have you here, and please, the floor is yours.
Thank you very much also for the introduction. I might be a PhD student, but you don't need to hold back in the discussion. You can take the gloves off. I fought many fights over this, so I think I've heard almost everything.
An interesting talk to listen to.
All right. Okay, so let's get going. So what I'm presenting here is some recent work we published in James now in December, I think. And at its core, it's about ocean modeling in Python and high performance ocean modeling in Python. And specifically, it also works on GPUs. And I will show you all the ins and outs of that, see how it works, and then we can see whether you like it or not, make up your own mind. So the title is JAX of all trades, master of some. So JAX is the library that we build on to achieve high performance in Python. And it's a compromise between many different things, but I think it also does some things really, really well. So yeah, you can decide for yourself if you agree or not. So let's go. So first up, I want to talk about the big F. Fortran. So most of you probably know Fortran a lot better than me. So I don't need to tell you what the strengths are of Fortran, and it does have a lot of strengths. But yeah, me personally, and I think a lot of other people are also recognizing that Fortran also has a lot of weaknesses that are not present in other languages. So what I show here by these arrows. So I think you can find lots of things that are suboptimal, but I think one very important thing is GPU support that is really lackluster in Fortran. Also, since Fortran is not used for machine learning, and machine learning is the #1 GPU use case today, it's a bit lacking behind. And yeah, another thing I want to highlight is and also the reason why I did this work is because I really like to use Python and I don't really like to use Fortran. So I think there should be something for everyone, and based on personal preference, you should be able to make a choice here. We also have a blog post that discusses all of these reasons in a lot more detail. So if you're interested in that, you can look at it. And there's another point I want to make is that even people that are very active in the Fortran community, I think, are now recognizing and acknowledging that Fortran does have a lot of problems, especially in the tooling space when it comes to building your project and package manager, the lack of a package manager really, and different hardware platforms. And hopefully this is all going to be fixed now that it's being recognized. But yeah, in the meantime, why not let's have some fun and do it all in Python and see how it works. So the way we go is a bit different from the traditional Fortran way. So in Fortran, you have most of your performance tools built into the language, so you can just build your stuff and then you're done for the most part. In Python, we have to build on a much deeper stack of libraries to get all the parts and at the performance that we need. So we build on NumPy and JAX for arrays, and you'll hear a lot more about JAX later. And for solvers, we use PETSI, which you could also use in Fortran, of course. And communication is also handled through MPI. And then you always have the Python wrappers for these C libraries. So PETSI for Py, MPI for Py, and then I co-wrote MPI for JAX. So we can use MPI operations from JAX. And the thing is, with all of these underlying libraries, in this case, XLA, which is the compiler that JAX uses, PETSI and MPI, they all by now have native GPU support. So you can operate on GPU memory just as if it were CPU memory. And things like MPI communications from and to GPU memory without it even hitting the CPU is now possible, even from Python. So I think that is a very nice stack that worked out very nicely for us. And what pops out is this ocean simulation, in this case, a 1 degree output. So if we integrate all of this stack, the result is Veros, which is our Python ocean model, versatile ocean simulator. Just to introduce it briefly to you, we took a Fortran ocean model called PyOM, which is like a reduced version of MOM or so, like an early MOM version. So it's not super high complexity. This is not Nemo or POP. So this has a couple of 10,000s of lines of Fortran, but it's still a reasonable complexity. So this is still a full primitive equation model in 3D and Z coordinates, but it doesn't really take that many shortcuts. So there's a lot of discrete parameterizations and closures, and you have everything, all the ingredients that you need to do realistic ocean modeling. And there's about 140 variables or so, just to give you an idea of what the scope is of this. And our really design goal was that we wanted to have something that's accessible, but it also runs on the whole spectrum of different hardware that you might have. So it runs on laptops, so students can run it like in the workshop on their own hardware. If a math student has a gaming PC at home, they can use their own GPU, which I think is really, really cool thing, and that excites some students. And we can also use it on clusters and really highly parallel architectures. Now, to give you some idea of how that might look, translating a Fortran model to Python, it might sound insane at first, but it's actually not as bad as it sounds. So the first step just boils down to replacing syntax. Since Fortran or Python array programming is modeled after Fortran, the semantics are usually the same. So all you need to do is translate syntax. And in a very stupid first pass, you can do this with like regular expressions. So you take do loops, write a regex for that turns it into for loops, and then you're almost done already with the first pass. And this is already runnable Fortran code then. So I had like a dozen or so regular expressions that just replace the syntax. And then it's almost runnable Python code. It's very slow Python code, but it works. And then you need to iterate on that and turn it into vectorized code, since I'm sure all of you have heard that Python code is terribly slow if you use explicit loops, similar to what you might find in MATLAB. So you have to rewrite all of this into array operations, as you could also do in Fortran, but often it's more natural to write things in with a loop. For example, this, so if we look at this example, here we have some Fortran code that does a loop in X and Y direction. And then for every element, it checks some condition. And if it's true, then it updates some array with some values. Since you have a condition here, this is a quite natural way to write this. If we turn this into array operations, then we have to introduce a Boolean mask instead of this conditional, then multiply it to the result to achieve the same effect, but this does strictly more work than this. So this skips a lot of elements where the mask is false, but this actually does the computation for all of them. So vectorized statements are more concise. I wouldn't necessarily say they're easier to read, that it's just less code. And they often do more work on CPU, so we have to pay a small price in terms of performance. And later we'll see how big the price is. But as soon as you've done that, now the real kicker is that you can really switch out the library that manages your arrays with another library and potentially get tremendous speedups, since we have all these accelerator libraries now pouring in from machine learning like PyTorch, TensorFlow, and JAX, that we can really switch out in the background without the user noticing, and then harvest these speedups. And this worked very straightforward for at least 90% of the code or so. So there's very little places in this whole Fortran code base where we had to think a bit harder about how to vectorize it. And in the end, everything worked out fine. So we could vectorize everything minus epsilon, but I might return to the epsilon later, but it's really not a big deal. And now, so Varus is actually a quite old project. It was, I think, 4 or 5 years ago that I started it as a master's student. And but that we have JAX support is quite recent. That only had landed a year ago. Since JAX is also a very new library. But JAX is really, I think, the optimum between being flexible and very performant. So if you do any modeling in Python, it might be a good idea to check out JAX and see what it can do for you. Also because it requires very few changes to your code. So I will actually show you now, I think. So let's not get into too much detail. Yes. So now I'm going to do something very stupid, which is do some live demo for you. It might backfire, but let's see if the gods are gracious today. And okay, let's go full screen. So this is a Jupyter notebook that is initialized with a very simple shallow water model. Let's see if we can execute these first cells. Okay, it seems to be alive. So this is the shallow water model. It's just these 3 equations that we discretize with finite differences. So it's really a very stripped down version of the full model. And so in Fortran, you might write these finite differences something like this. So you have a loop over the spatial dimensions. And then the gradient is something like shifting these loop indices by 1 element. In vectorized language, this reads like this. So instead of having integer index shifts, we now shift slices. So we have an overlap cell at each side of the array. And so the original array is like this slice 1 to -1. So you slice away the first one and the last element. So this is the original data. This is unshifted. And then to get this j+1, you shift this slice by 1. So instead of from going to 1 to -1, you go from 2 to the end. So this is just this operation in array language. And if you write everything like this, then you end up with a step function like this. So this is just these 3 equations. implemented here. This is a shallow water model, I think on a staggered C grid on an F plane or so. So it's not the very simplest model, but almost. And then we specify some initial conditions like a Gaussian bump somewhere in the domain, and then we'll run the simulation. It is very fast. This is just using NumPy now. That's a small problem, so it works fine. Then we can do an animation of the results. Okay, and this is how it looks. So we have this bump here that stays behind because we're on an F-plane, and then we have a Kelvin wave running around here, and then the rest is just gravity waves. And what I actually wanted to show you now is how we can change this code snippet to use JAX and see what the speedups are that we get. And to really prove to you that JAX, going from NumPy to JAX is actually quite easy. So the first step we do is, I think I will restart this kernel so we don't get anything. Okay, so instead of doing NumPy as importing NumPy as NP, we import jax.numpy as JNP. And really the biggest adjustment will be to replace all of these NPs with JNP then. So over here. And then another thing that we have to adjust is one implementation detail is that JAX arrays are immutable. So you cannot change them in place. So we need to use a different syntax, which is this. So we use, you have to assign something on the left-hand side on all operations that you do. So that also required some changes to our data model. Okay, so we have this, and then we have that. And then we do the same here. Since JAX arrays are immutable, we don't need to copy anything. And then we do the same here. Change these functions here. And this should be the last one. Let's see, maybe I forgot a numpy something somewhere, but we'll find out very soon. Whoops, here we go. Okay, there it is. Yeah, so here I forgot one too. Yes, here we go. Okay, that works. This works, that works. And you can look at the timing here. So before the changes, we had like 1,000 model iterations per second. Oh, I forgot the most important part. So by default, JAX just does eager evaluation, which is not what we want. We want to actually compile this function to machine code and then execute this. So we want to add this compiler step, which is called JIT for just in time. It's a just in time compiler. So we apply this compile step here to this function and mark this as we want this to be compiled. This is where the real performance comes from. Okay, so now again, before we got 1,500 iterations per second or so, now we get 2,000. If I execute it again, we get 12,000 because it has to compile it first in the first run. Okay, so now we have 12,000 iterations. It's, I don't know, 10 times faster. So we can also go to a bigger problem and the payoff will be even bigger. So if we increase the size by a factor of 100 in the model, then we'll also get, yeah, this is actually, I think it was already pretty fast, pretty efficient before I changed it. So now this is 100 times slower as we would expect. And with NumPy, this would take a couple of minutes, and now it takes 10 seconds to do. And all we did was change this function definition. It still runs on CPU. This is, and it's pretty much the same code that's running. And this is my backup that I didn't need. Yeah, and then you can do more fancy. We have a lot of examples here. This uses actually a distributed execution, so you can run it with MPI run and with JAX and on GPU. So yeah, we can try that. Or actually, why don't we just for fun switch to GPU here? Or I think I'll have to restart. We can switch to GPU. I'm actually executing this on a cluster node that has some pretty big GPUs, Tesla P100s. Not the biggest GPUs, but some of the biggest. It's probably not going to be a big speed up now since the problem is quite simple, but just for fun, we can see what we get. So now just by changing this flag, now I'm running on GPU. If it works. Maybe not. Okay. I probably messed up my missed loading some modules or so. Okay, I died. Yeah, I missed some loading some modules, but let's get back to the presentation. I'll show you the numbers there. But that is the rough idea. Oh yeah, just a second. I have to exit full screen for some reason. Okay, so we're back to the presentation. Okay, so that was the demo. Here's more backup that we didn't need. Okay, oh yeah, another thing I wanted to show you is a big reason why we wanted to do it in Python is because the model ergonomics, as you might call it, are so much better. And something like this would be extremely hard to pull off in Fortran, I think. So I want to show you how simple it is to install Varus and get running on GPU from almost zero. So you have to have a working Python installation and a GPU setup, which is of course a problem in itself. But then this is a screencast, how simple it is to get started with Varus, also for students in a workshop or so. So first up, but this is in double time, so it's not quite real time, but almost. So now Varus, the command isn't there, so to show you that it's really not installed. And to install it, just type pip install Varus, and it pulls it from the Python package index and installs all the dependencies and installs Varus itself. That takes a couple of seconds. And now it's installed, and we also install JAX because we want to run on GPU. You don't have to use Varus with JAX, you can use it with NumPy if you're fine with it running slowly. So students usually use NumPy and don't bother about JAX. And now we can use the Varus command line here. And right. So in the first start, it's a bit slow, but then second and subsequent starts is much faster. And then this was a bit faster. This GIF is a bit jumpy. Let's see if I can show you. Maybe. Okay, here you go. So, and then how you run Varus on GPU is just you do Varus run, and this is like a setup file that contains all of your model settings, like a name list in the Fortran world. And all you need to do to run on GPU is you give like -b JAX, so backend JAX, and this is unfortunately cut off, but it's like -- device GPU. So it's just a runtime switch, and you can seamlessly switch between CPU, GPU. There's no need to compile anything, recompile anything. And this is, I think, makes for a really nice ergonomics of the model. And it's really, I think, a pleasure to use for me at least. So this is a summary of what I just showed you. It's actually quite simple to write if you get used to this index shift notation. Now that we have MPI for JAX, it also scales to pretty much any number of devices. So you can just use your already MPI parallelized model, translate it to Python, and keep on using MPI in all your domain decompositions and whatnot. And it's quite simple to run on any hardware. So you just change these flags from CPU to GPU, or you use MPI run to run on multiple processes, and you get these speedups. And then this is a more complicated shallow water model, nonlinear one that we use for testing in MPI for JAX. Okay, so the remaining question is it actually fast if we apply this recipe to the whole model? And this is a slide I presented at AGU last year. And I think the answer is yes, or at least faster than anyone thought. So on CPU, I actually get into this. So this is just a summary slide. So on CPU, we get very close to Fortran. On GPU, we get really nice weak scaling. And as a proof of concept, we also ran this on, we did a 0.1 degree eddy resolving global setup that we simulated only on 16 GPUs on a single node. So instead of using, I don't know, 2,000, 4,000 CPUs distributed over many nodes, and you need a whole cluster setup, we just had this one cloud instance, GPU instance, that was running on a single node, so you didn't have to worry about interconnects. And it just, yeah, these 16 GPUs connected to this one node that produced this 0.1 degree simulation in, I think we got a year a day, so a model year per day, which is also, from what I've gathered, is good performance, even if you compare to many thousands of CPUs. Oh yeah, and here's an animation of the spin up of this 0.1 degree year. So yeah, to get a bit more into the details. So this is the CPU performance from this slide. And you can look at the relative speed up here, for example. So with JAX, this is the number of MPI processes. So this is the number of CPU cores. And the maximum here is 256, which might sound low, but this is a 1 degree model. So typically we'd run this on like 96 CPUs or so, at least we do. So as you scale to multiple CPUs, multiple nodes, JAX falls off a bit. So this is about a 30% or so performance loss of JAX compared to Fortran. But if you go to few CPUs or many CPUs, it's comparable or even better than Fortran. But yeah, I think even a 30% performance reduction is acceptable in many cases if you save a lot of human time in the process. And you can see that with NumPy, it's hopeless to catch up to Fortran. So we have like a factor of 7 or so here between NumPy and Fortran in the worst case. And then if you go to a very high CPU counts, it catches up, and it's like a factor of 4 or so. But it's not really anything you would want to use for operational modeling. And yeah, what we're the most proud of is, I think, the GPU performance. So if you do strong scaling, so you keep the model size constant and just add more GPUs, it doesn't scale very well at all, since GPUs are quite sensitive to being fully utilized. So you want to really put as much data into the GPU as possible so you can do very massively parallel operations. So the strong scaling is not very good, but if you manage to really fill out your GPUs, and this is weak scaling where we keep the model size per GPU constant, then you can get almost perfect linear scaling with this. So this, I don't know, maybe a 5% loss or so. So this is actually very, very good scaling. And you can look at the absolute numbers here. So this starts at like here 10 to the power of minus 2, 2 to the power of minus 2. So this, it starts somewhere here, and then yeah, it goes all the way down to here or so. So this is much better than this CPU setups. One GPU is something like 200 CPUs or so. And again, this is our 0.1 degree setup. So it takes about 600 gigabytes of memory. So this is not a trivial setup in any way. And we did it on a single cloud VM with these 16 very expensive GPUs, but you actually save at least a factor of 3 in energy. And I can't measure it, but my estimate is that it's at least an order of magnitude more energy efficient than a comparable CPU simulation. How are we doing on time? Probably running out soon. So
we started 5 minutes late, so you still have at least 5 minutes to go.
Okay, that's great. Yeah, I think then I'll manage. So I don't want to hide that there are many problems with using Python for this. So I showed you many of the advantages, but there are also several problems. And I think the biggest one, at least for me, is that we have no good way to write these models yet, or there's no established way. So in Fortran, people have been writing models since, I don't know, what, the 70s. So we really had enough time to agree on one way that we want to write models. And it's also much more restrictive language. So there's not that many freedom anyway. There's not that much freedom anyway. But in Python, we have too much freedom and too little standards. So it was quite frustrating for me to figure out one way to write this, but also considering all the other ways we could do it. And it's not really obvious which one is good. So something that we really dream about is maybe separating physics from numerics, like instead of doing these finite difference operations that are like hard coded into the physical routines, what if we could say something like, let it figure it out automatically, which schemes to use, and just describe the physics that we want to do. So this is just a simple multiplication on different grids. I don't know, something like this, like on the T grid, or interpolate to the T grid and then multiply these two quantities or so. And this could translate in the background to this. And luckily, the dynamical nature of Python really gives us all the tools that we need to build something like this. So I think this is very much within reach, but abstraction is also a much harder problem than just writing something and making it fast. So I think this really has to be a community effort where people really put their heads together and think about what are the ingredients that we need for something like this and then build something. But I'm also pretty sure that if more people start doing modeling in Python, this is something that is going to happen and that the community is really good at. But yeah, it's one thing where Fortran clearly has an advantage. And for the last slides, I want to show you some other cool stuff of what we can do with it. So we got a bonus almost by accident. We didn't really choose JAX specifically for this. We chose it because it's fast and it works well with our data model and was easy to integrate. But JAX code is also natively differentiable. So you can do auto diff through the physical routines. So this is an actual example from Veros. So we have this function that gets the HTT, so it's part of the equation of state. And you can evaluate this function at a point for salinity, temperature, and pressure, and you get a result. But we can also ask for the gradient of that function. So we do just jax.grad, apply it to this function, and say in respect to what, in this case, salt, and then evaluate the gradient and get the answer for the gradient. So by accident now, almost all of our model is numerically differentiable just by asking for it. And there's actually some really cool things that you could do with that. So one obvious thing is integration with machine learning. So Julien just had a very nice talk yesterday where he motivated this. So if you can have a differentiable physical solver in your training loop, this actually opens up a lot of possibilities. Yeah, so there's some ideas in this review paper, and one of them could be like you could train mappings of parameters, input parameters, parameterized by a neural network before even putting them into the model, and then train it end to end so it matches observations or so. You can do emulation and subgrid scale parameterizations. So you can do something like, yeah, so here this is a paper where they do the by now well-studied problem of turbulence closures or learned turbulence closures. And in this case, you get like an 80 times speed up. And for this, you also need a differentiable solver. Also for the work that Julien showed yesterday with a posteriori trained turbulence closures, you do need differentiable solvers. And but what I personally am most excited about is can we use machine learning to make discoveries, not just to make our models faster or more accurate, which are noble goals in its own right, but can we actually make scientific discoveries using machine learning on models? And I think that answer is yes, because there's so many things that we don't understand that happen in models. I don't understand them. So stuff like what are causes of events? So can we do causal inference, causal discovery on the model to find out what the causes are in the model for something like El Nino or hurricanes or whatever we see in the model? Can we trace information propagation, I don't know, between Greenland and Antarctica? Can we find the pathways of that? Can we do anomaly detection unsupervised maybe? Can we search for tipping points in the climate or something like what would we have to change in a model to eliminate something like a double ITCC or so, which I think are super exciting questions. And I think machine learning has really good potential to make headway on those. And I think differentiable models could actually be a really critical piece of the puzzle here. So yeah, if this is exciting for you, I urge you to think about these questions, because this is what where I see the meat of machine learning contributing to science, really. And yeah, that's it from me. Almost on time, I think. And thank you very much. So this is our paper. It's called Fast, Cheap, and Turbulent. It just published in James. And if you want to know more, hit me up on Twitter, write me an email. Of course, now ask in the chat. And this is the URL for Veros if you want to try it out. I think it's a great tool for students, but also for research applications where you want to do very dynamical studies, want to change the topography of something or so, like crazy ideas. And for that, it's really nice. Yeah, and then otherwise, I'm happy to hear questions. Thank you.
Thank you very much, Dion, for this talk, and indeed, pretty much on time. I think we'll have a number of discussions here, and I think you're opening interesting avenues here, and all in the room can guess why. I was very happy to invite Dion to talk and give this presentation today. So we have indeed quite some questions already in the chat. The first of them by Anne-Marie, talking about the acceleration with JAX versus the acceleration with NUMBA. Could you maybe, Anne-Marie, rephrase your question or formulate it?
Yes, I mean, it was just a simple question on the shallow water example. I mean, was it a fair example? Because you could also have added only one line using NUMBA to compile your function, and wouldn't you have got the same acceleration by about a factor of 10?
Yes, so we actually investigated all of this. There's a repository that we made, or that I made. I can post a link in the chat where I compared NUMBA and JAX and TensorFlow and PyTorch and I don't know, Isaura and like some more esoterical options. I wrote it now. So I took some subroutines of Veros and implemented them in all of these backends and then tested the performance. And you're absolutely right that NUMBA is pretty much the king of CPU performance. So I could not measure a difference between NUMBA and Fortran, for example, for these routines. So NUMBA is extremely good, but there's a but. So one thing is, for NUMBA to really work well, you need to stay with your explicit loops. So if you have a fully vectorized code, NUMBA acceleration is a lot worse than if you have it written in the Fortran loop style. And that's a problem for us because then you're like committed to using NUMBA. You can't just use something else because you have to write your code in this specific way. Another problem is NUMBA does have GPU support, but it's not really GPU support because you still have to write CUDA code, but with NUMBA syntax, and it's really awkward and not good. So if we actually seriously consider to say, okay, forget about GPUs, we're not really interested in that in this stage, and let's just use NUMBA and have something that has Fortran performance on CPU, but it's a Python model. But really, now that we've done this work, I think this would leave too much on the table because GPUs, I was blown away how well it works. And I think it's really a modern high performance model will have to support GPUs at some point because they're just too good to ignore.
Thanks a lot for this first exchange, indeed. We now have a question by someone from the Mercator Ocean access point. I don't know who's speaking here. Talking about the performance of output.
Sorry, this is Jérôme Chanu from Mercator. Yeah, a simple question about the strategy to read and write in Python efficiently, because this was a bottleneck for us some years ago. So I suppose that it is costly also in Python. And, do you have idea about that?
Well, not really. You probably know a lot more about the bottlenecks at these very large scales. So for now, we've run on. So we did this. Well, okay, let me separate that. Like on CPU, we've never gone beyond, I don't know, 200 processors or so. And that's not really a bottleneck. So we just write netcdf file through the regular netcdf parallel library, and we don't do any special measures to speed that up. probably you could apply the same recipes that have led to speedups in Fortran models also to this model, since we use the same libraries in the background, and I don't see why that doesn't work. But then again, I don't know much about it. In the GPU model case where we did the 0.1 degree setup, I think that's also one of the good things about GPUs. So one thing you can do is you just copy, every time you want to do an output, you just copy everything to the CPU, which is costly, but it's not that costly. Then the CPU can write it to disk, and in the meantime, the GPUs can continue with the simulation. So you can really do this fully asynchronously in this case. So you have the CPUs dedicated to writing output and the GPUs dedicated to integrating the model. And I think this is also something that it would be great to do, like benchmarks on this kind of workloads and see if you can solve some of these problems this way. I think it would be really nice to do.
Thanks for this exchange. Indeed, the cost of I/O is something that is becoming a main limiting factor for large applications, and we've discussed that already. Next question by Alex Megan about the differentiability.
Hi Dion, nice talk. The thought occurred to me when you said that JAX is natively differentiable. Has anyone thought about the possibility of using that to generate an adjoint to the code? Because I know there are tools that people have used, possibly at MIT.
Yeah, again, this is not a topic that I'm really an expert on adjoint models. So I don't really know what the requirements are for an adjoint model to be good. I know that, for example, MIT GCM, I think it also has like handwritten numerical differentiation. So this autodiff would be quite similar to that, only I heard it's quite buggy in the MIT GCM code. So it would be hopefully less buggy and just work without having to write it by hand. It's still not a, so how should I put that? It's not completely free. You still have to think about some stuff, especially if you unroll over long iterations, your gradients become unstable and then it's pretty much unusable. So you have to do advanced techniques, and there's a lot of development in the Julia ecosystem in that direction, like really advanced autodiff techniques like shadowing or so. If you have chaotic trajectories, I don't know, you sample several of them and then do some magic on that to get more accurate gradients. But in general, I think it could fill at least a similar role as an adjoint. And there's probably some literature on how to replace adjoints with that. But I'm not confident enough to say that it's the same thing.
Okay, thank you.
If I may just comment on this, this is really much related to what we've discussed on day one with Nora Luz, and indeed there's lots of work in the Julia community with this project DJ for Earth that is starting. But if you're looking at small problems, formally the objects we're talking about are exactly the same. So indeed, with the autograd, what you would get in the end is an object that is very similar to an adjoint. Next question by Bob Alberg.
Thank you. That was indeed a provocative talk. One of the things that we do in kind of more modern ocean models is things like vertical remapping or fully general rotation of the mixing tensor, where you can't write things down as a sparse matrix operation where you know beforehand which layers are mapping onto which other layers. So for vertical remapping, any layer can remap into any other layer. And so to do it with a matrix, you have a full n squared dense matrix, potentially, even though most of the entries are 0, and we write our Fortran code in a way that takes advantage of that. Is the approach that you're describing here something that is going to have problems with that sort of algorithm?
Yeah, I'm happy that you asked. I mentioned it worked well on the whole model minus epsilon. So now we're at the epsilon. So one example that we encountered is, I mean, something much simpler, but it's essentially the same problem where you have, we do tri-diagonal solvers in some implicit schemes in the vertical direction. And there you have the same problem that you don't know the matrix elements, or they just change between the iterations. So you can't really write this in a vectorized way that performs well enough. But JAX gives you one more tool that you can use in this case. So you can handwrite your algorithm in low-level code. In our example, we wrote it in Python on CPU, and we had a student write it in CUDA for GPU acceleration. So we have this, I don't know, it's maybe like 20 lines of C code and 20 lines, maybe 100 lines of CUDA code. And then you can wrap these with JAX as a custom call, and then JAX can use it natively in its computational graphs. So you have this option if it's only a very small part of your model, in this case, it's 0.1% or so of the code base, that you cannot vectorize, then you can still write it by hand. You could also write it in Fortran. And then bind it to JAX, and JAX can use it as if it were XLA code. So in this case, I think you can get the best of both worlds. Of course, if it's like 30% of your model, probably not going to be worth using. But if it's a very small part, it works beautifully.
Thanks for this exchange. That's a lot. We get lots of questions here, so I'll take 3 more questions and then we'll break. And those of you who are interested would be kindly invited to stay here for an extra Q&A session. So we now have a comment by Jan Zika, I think.
I just wanted to make the comment that there's a few interesting projects which use Python and simulate fluids in a spectral way. There's one called Daedalus, which I think is getting quite a lot of traction, which kind of is, and in those projects, they're based in Python, and you actually write the code, you write down the problem mathematically, describe the boundary conditions and what equations you want to solve, and then the numerics are dealt with under the hood. So I think there's a bit of work in that area, but it was a really great talk. I was really impressed by what you're able to do, and I think it's really exciting.
Yeah, thank you very much. I also know about these projects, and there are some more, especially in the finite element space. You have something like Phoenix or so, where it's a bit more popular since the math is so much more complicated. And I agree, there's some good approaches, but there's not really one thing where we could say, let's just all use this and we never need to use anything else. So there's like no established community standard. But yeah, there are people doing work in this direction, and it's great that they do it.
I think it'll be difficult if from let's say an operational climate or ocean modeling point of view, because the level of detail that the groups like DRAKKAR and other groups go into in terms of, we actually need to remove this island because we've got some numerical problem, or it's a bit harder to sort of imagine that. So I think that's great from a kind of, a student level or a very like theoretical project where you're thinking, okay, what happens if we have flow over a bump, or, and we push it to a high resolution. But when you have something operational where the real details, then more the approach that you described where you actually have a hand-coded model, but you could still speed it up in Python. I was really, really impressed by,
Thanks for this exchange. One more question by Mike Bell.
Thanks, Dion, for a really exciting talk. I'd just like to hear you say a little bit more about the MPI support within JAX and how much effort it takes to put in the sort of the data exchanges that your models typically need.
Oops. Yeah, sure. Actually, not much. So yeah, here you see it a bit.
Yeah.
So the way this works is we wrote MPI for JAX, which also uses this custom call mechanism that I mentioned earlier. So now JAX knows about MPI functions and can use them just if it were built-in JAX functions. So you can just do this MPI for JAX dot, in this case, send receive, and it's the same signature really as in C or in Fortran. So there's really no difference. I mean, if it comes to like stuff like domain decomposition and where do you put your data, and so then it gets complicated. But really the underlying primitives are exactly the same. as in the C and Fortran case. And if you build your MPI library with CUDA support, for example, it can automatically read from and to GPU memory. There's no, you don't even need to tell it this lives on GPU, so it just knows. So there's really nothing you need to do. So if you build, have a MPI that's already built on your cluster, so then you just do pip install MPI for Pi, MPI for JAX and Veros, and then you can run Veros with Slurm or whatever you want to do. So it's really just works. So that's kind of magical to me when it first worked, but yeah, it's quite easy actually.
So it's very easy to translate the original Fortran code into this.
Yeah, the MPI part is just one-to-one. You need to make 0 changes.
Yeah.
And probably the last question before we break, Chris Wilson, please.
Hi, thanks, and thanks for the very inspirational talk. I was just trying to play around with the idea of what the future might look like, provoked by your interest in what scientifically we can learn from machine learning certain questions. So at the moment, we're probably already there. We're running models maybe once, and they're very expensive. They're generating so much data that we're struggling to analyze the output. I just wondered if maybe there are several answers, several possible futures. Might it be a case where we're less interested in the generating lots of output because it'll be hard to analyze, and it's more about asking a question which we can diagnose on the fly, and because the models are so easy to run in the future?
Yeah, maybe we don't want to, for some questions, we might not even want to output at all, and just feed it to some other dimensionality reduction or so, and then just look at the output of that. So maybe your pipeline just gets longer, or you just use the physical model as a part of a bigger, maybe machine learning, maybe not, a bigger system that then condenses it. I don't know. Yeah, or if your model is very fast, then you can just run it on demand, like, and it doesn't matter anyway. Why write output? But yeah, I think it's a while until we get there.
Thanks.
Well, thank you very much. We will probably, I mean, there are probably some more questions in the chat, but I suggest we stop, and then people may stay in the room for discussing. So with this, I'd like to thank you again, Dion, for this talk, and thanks for the great exchanges we've had here. Lots of questions, and indeed a very provocative talk. Thanks a lot for being here. And those of you who are interested are more than welcome to stay in the room a bit. I'm stopping the recording now. Thank you.
Thank you all, and thanks for the questions. I think it was a very nice discussion. It can't have been that provocative. I didn't get any insults this time. So.